Okay, welcome back. Last time we talked about some basic kinematics terms. We started off with position, where an object is in reference to some origin or reference frame. We talked about distance and displacement, which are different things. Distance is the total length of an object's path as it moves. Displacement is simply the straight line length from starting to ending spot or initial to final position. Those do not have to be the same. We talked about what time is, just kind of helps us order a sequence of events. We measured it in seconds. And then we talked about speed and velocity and how they are also different. Speed is how much an object moves per unit of time. It's distance over time. Whereas velocity is how much an object's position changes over a period of time. And that is displacement divided by time. And I'll just kind of box in the equations here that might be kind of useful to you. So here's the equation for displacement. And here is the average speed and average velocity equations. Okay. And the reason I box those in is because they don't show up actually on the reference table. I'll give you a look at what does show up on the reference table a little later in this video. All right, quick example of the difference between speed and velocity. Very similar to the difference between distance and displacement, and then we'll move on. Let's say that you are a runner and you do one lap on the track in 80 seconds. To find your average speed, you would simply do this, okay? You write down the equation, average speed equals distance over time. The distance, if you're doing one lap on the track, is 400 meters. And if the time is 80 seconds, then all we do is 400 divided by 80, and we get 5. And the units of that are meters per second, okay? This means that on average, as you went around that track, you moved 5 meters every second. That's what a speed is. On the other hand, your average velocity would be given by this formula. V hat equals delta x over t. And remember, delta x, the displacement, is final position minus initial position, x minus x naught. Now, it doesn't tell us exactly what the positions are, but in a lot of cases we can make very simple inferences. Let's say that the initial position, and we do this a lot, let's just say it's 0. Okay, let's say you start at the origin. You start at where the reference frame begins. You start at 0 meters. Well, if you run one lap, then that means that you're coming back to 0 meters. So if your initial position is 0 and your final position is 0, then the difference between those, guess what, is also 0. And this is just a little trick that we use. If something is 0, you can, you don't have to substitute in. You can just put like a little arrow and write 0 up there. So this would end up being 0 meters over 80 seconds. Delta V is 0 meters per second. That is actually your average velocity. Over this time period, your position didn't change. The displacement was 0, so your velocity was 0, because your velocity is the rate of change of an object's position over time. The rate of change in the position, since the position didn't change over this time interval from beginning to end, ultimately, is 0. Now, yes, we know that the position changed during it, but since the runner got back to the initial spot, that means that the displacement was 0. Therefore, the average velocity for that time period was 0. It's important to know the context, whether you're looking, if a question asks you to find the average speed or the average velocity, because those are often different. We're now going to define acceleration, okay? Now, a lot of times, I read a quote once that said something to the effect of understanding physics is like learning a language that sounds a lot like English, but a lot of the words have different meanings. I wouldn't necessarily say different meanings, but they have very precise meanings, and those meanings are different than you might say when talking to a friend. You might use interchangeably speed, velocity, and acceleration when talking in a non-physics context, but in physics, those all have very specific definitions. While speed and velocity show you how much an object moves per unit of time or how much an object's position changes over time, Acceleration does not tell you either of those. Acceleration tells you about the rate of change of velocity over time. And there's an equation for this. So instead of telling us about the change in position over time, now we're talking about the change in velocity. Not every object moves at the same velocity. Matter of fact, some objects change their velocity as they move in certain circumstances. So what we're looking at here is we're looking at an object that's velocity has a changing velocity. If you were to measure the instantaneous velocity at different points, they would be different. Now, this is opposed to something that would, let's say, has a constant velocity in which the instantaneous velocity is the same at all points in some time period. The equation for acceleration, I call it the definition of acceleration, is actually right, you can kind of understand it right from here. Anytime you see rate of change of something, that means you're going to have this delta symbol, this triangle. That symbol means change. So the acceleration of an object is equal to delta v for velocity over t. And anytime we have a delta something, that always means how much it changed from its its initial value to its final value. But we always do final minus initial. It always comes in that order, final minus initial. So another way we could write this, just like we had delta x equals x minus x naught, we could write it like this: v minus v naught over t. The acceleration is the final velocity minus the initial velocity over time. Since we're dealing specifically with velocities, acceleration is always a vector. And the units are meters per second squared. And you can kind of understand that because the units up top here for velocity, those are meters per second, and you're dividing by another second. So you're going to get seconds squared on the bottom. Okay, those seconds don't cancel out. It's going to end up being meters per second. Now, acceleration, it means, okay, change of velocity. And velocity is how much an object's position changes over time. But remember, velocity, since it's a vector, that means that not only does the size of the measurement matter, how fast something is going, but also the direction. If you're describing a velocity, you need to describe not only the number of meters per second, how fast something is moving, but also what direction it's moving in. If you're just talking about speed, you actually don't have to, you shouldn't tell me what direction it's moving in, okay? Velocity, a full description of velocity requires you to tell me not only the size of the velocity, but also the direction. So let's think about how an object could change its velocity. How could the velocity of an object change? Well, one way it could accelerate is to speed up. And there's actually 3 different ways. I'll list them right now. There are 3 ways for an object to accelerate. Well, it could speed up. It could start moving faster, so it's covering more meters per second. The second one, if we have speed up, is kind of obvious. The second one would be slow down. Okay? It could start covering fewer meters per second. The third one is not quite as obvious. Sometimes people say, oh, well, it could stay the same. Well, but then an object wouldn't be accelerating because the velocity wouldn't be changing. Okay? The quickness that isn't that wouldn't lead to an acceleration. We're looking for something that changes the velocity. Okay? You could speed the object up, make it move more over a greater displacement in a certain amount of time. You can make it move over a smaller displacement in a certain amount of time. You could also, since velocity is a vector, and vectors have magnitude and direction, you could also just make the object change direction. An object that is changing its direction is accelerating. I'm going to put that one in stars because everyone always forgets this one. Okay? Objects that change direction are accelerating. Now, I just want to make one last note about acceleration before we move on. When we talk about acceleration, okay, you could keep going down the rabbit hole with this. You could say, well, what if is there a term for like how much the acceleration changes over time? And there is. It's called jerk, technically. But we're not going to talk too much about that because we mainly deal in this particular class with constant acceleration. I'm not saying you'll never see a changing acceleration, but we mainly deal with constant acceleration when we're dealing with math problems. So for and I'll get to what that means in a second, for mathematical problems. Now, you might have a situation where the acceleration might change or might vary between periods of time but that change is usually not continuous. In other words, you won't have something that the acceleration is something different every second. You might have something where the acceleration, let's say, is like 5 for a certain amount of time, and then snap your fingers, okay, now it's 2 meters per second. But you won't have something that like smoothly changes its acceleration usually, and especially in this early on part. So we've defined the basic kinematic quantities. That's really the basics of kinematics. We are studying distance, displacement, speed, velocity, and acceleration. What we're going to do now is see how those variables are related to each other through equations. Now, these equations, we will spend some time in class going over where the equations come from and what they mean and how to use them. I'm going to give you the basics here, but I'm going to give you the 3 main kinematics equations. Now, you've already had a few of these equations, okay? You've had what I like to call the definition equations. We have so far defined, let me just do this. We have defined for you average speed, average velocity, and acceleration. What we're going to do now is see some other equations that link together these different variables. And we're actually going to start with the acceleration definition that you just had. That's a equals v minus v naught over t. Now what I'm going to do is I'm going to rearrange this so that v is all by itself. I'm going to do some algebra here. The first step is to, let's get rid of this fraction. Let's get t to the other side. How would I do that? I multiply both sides by t. That would give me a times t. I'm not going to put a multiplication sign between them. It's just a times t equals v minus v naught. And to get v by itself, I'm now going to add v naught to both sides. That'll cancel the v naught out over here, and I'll add it over here. And then I'm just going to rearrange so that the v is over on the left, everything else is over on the right. Here's what that gives me. It gives me this. V equals v naught plus a t. What this equation says is that the final velocity of something is equal to the initial velocity plus the acceleration of the object times the amount of time it accelerated for. And also notice, I want to make a point that all these equations that we're about to write, they assume, in other words, you have to have a constant acceleration in order for these equations to work. Anyways, this is the very first equation that appears on your reference tables. Your reference tables look like this. This is the equation right here that we just derived. I will explain what these x's mean in a future video. Don't worry about those for right now. This is the little 0 is the naught that we talked about. So v equals v naught plus a t. Again, I'll talk about what the x's mean in a future video. Another equation that we have is actually the next one down, and in class we will hopefully I'll have some time and I'll show you exactly where this equation comes from. The next equation down is this one. X equals x naught plus v naught t plus 1/2 a t squared. If you're thinking these equations look really complex, all you're doing is you have 3 different terms and you're adding them all together. The terms might be just a single variable. They might be a multiplication of a few different variables, and there might be a squared attached to it. These are very simple equations. There's no sines or cosines right now. There's no logs. There's no, there's nothing really crazy. It's all stuff that you've been able to do for probably 2 or 3 years. So this is another equation. If you've had another physics course before, and you've learned other ways of writing these equations. For instance, if you took Regents, this is the same exact equation as d equals vit plus 1/2 at squared. If you've had another course, I just need you to get used to these new variables. These are the exact same equations. Matter of fact, this is better actually because this equation allows for there to be an initial position, whereas the Regents one did not. The last equation I'm going to teach is this. V squared equals V naught squared plus 2ax minus x naught. Again, if you've had another physics course, it's just going to be a small adjustment to get used to these equations. I would really like you to use these equations and not use other equations that you may have used in previous courses. That means that you're going to have to get used to these new variables, and the easiest way to do that is have the reference tables out. Okay? Have the reference or the equation sheet or reference tables, whatever you want to call it, have it out when you're doing these homeworks. Okay? And again, don't worry about the little tiny x's. I will talk about those in a future video. They're not really important to you right now. There's one more equation that I do want to show you, and it's a new equation, and it's actually not on the reference table. So, things that you should have, that you should memorize, that you should work to memorize. Definition for average speed, definition for average velocity, acceleration, definition of acceleration. So, these three. These three you don't have to memorize because they're right on the reference tables. Here's your new equation that you should memorize. Remember, this symbol means average velocity. Another way, now we already know average velocity is displacement over time, but there's another way to calculate it. Average velocity is also equal to final velocity plus initial velocity divided by 2. And by the way, usually you will not have to remember a bunch of equations. You don't have to memorize them, but just the way that they wrote the reference tables, you do have to kind of memorize these. If you've had a physics class before, you've probably got these mainly memorized. You might need to switch around some the variable names. That's about it. Let me explain a little bit about this equation. This equation is useful if the acceleration is unknown but assumed to be constant, and if v and v naught are both known. So again, we will spend more time seeing why these equations work and where they come from. Right now I'm just kind of showing them to you. But I promise you, they're not just magic equations that happen to work. There are physical reasons why these equations have these certain shapes or these certain forms. You'll also notice that some variables don't appear in certain equations. So for instance, the first one has nothing to do with position. It's all velocities, acceleration, and time. The second equation, well, there's position, there's an initial velocity, time, and acceleration, has nothing to do with a final velocity. This third equation has nothing at all to do with time, and this fourth equation has nothing to do with, well, position, acceleration, or time. Okay? So you use these different equations in different situations based on the information that's available to you. Let me give you an example. First question, an object moving at 9 meters per second experiences an acceleration of -3 meters per second squared until it is brought to rest. How far does the object travel during this time? So let's label what we're given. The object is moving at 9 meters per second. Sounds like a velocity, and then it's brought to rest. The final velocity is 0, so I'm going to write over here v equals 0 meters per second. That means this must be the initial velocity, so I'm going to write v naught. This is the acceleration. We're looking for how far the object travels. It doesn't ask us anything about the time. It says during this time. We don't know what time that is. We're asked how far does the object travel. That means we're looking for x, its final position. And we can look for the final position if we make one little assumption. Let's make the assumption, because we weren't told otherwise, that x naught is 0 meters. The initial position was 0. Let's say it just started from 0. We don't have any evidence that it didn't, so we can start there. Okay, so now I just need, I know v naught, I know the initial velocity, I know the acceleration, I know the final velocity, and I know the initial position is 0. I'm looking for the final position. I go through my list and I look to see which will work. Now let's see here. This equation won't work because we don't know anything about the time, and that's not what we're looking for. Plus, we don't have x. This equation, same thing. We don't know anything about the time. Third equation looks good. Fourth equation, yeah, that's not going to get us any information about x. So the problem-solving process is I immediately write down the equation that I want to use. Okay, I look and see which equation I could use. I write it down. V squared equals V naught squared plus 2a x minus x naught. Anything that is 0, you are allowed to cross off as long as you write 0 above it. So like final velocity is 0. I'm going to do this. I put a little arrow there. I write 0. Same thing for initial velocity. You have to write it in the initial equation. You have to write the full equation out first. Then you can cross off and write 0 if there's anything like that. So I have 0 equals, let's see, this would be 9 meters per second. You must include units, squared, plus 2 times the acceleration is negative 3 meters per second squared times x. Okay. Notice that then once this went to 0, okay, x minus 0 is just the same as x. So what I'm going to do is just a little bit of math. This is going to be 0 equals 81 minus 6x. 2 times negative 3 times x is negative 6x. 9 squared is 81. To solve for x, I bring the 6x to the other side. 6x equals 81. Divide both sides by 6. I end up with 13.5, and I do need to put I need to put units on the end, so this would be meters. Like that. Okay? There you go. It means in this case, with this particular object moving this fast with this acceleration, this final velocity, the object must have moved 13.5 meters as it came to rest. You can literally test that in a lab and see that that's true. Let's try another one. This one's going to be a little bit harder. An object starts at rest. Anytime you see at rest, that means one of the velocities is 0. Since it's starting at rest, I'm going to write v naught equals 0 meters per second there. It accelerates for 6 seconds. That's the time. At this time, the object is at 72 meters. That must be the final position. What's its final velocity? And since it starts at the origin, that means x naught is 0 meters. We're looking for the final velocity. Now the issue here, okay, the way I would think to solve this, there's a couple different ways you can solve this, but the way I would think to solve this is we don't know what the acceleration is. And the acceleration is key for all of these equations right here, the main kinematics equations. Can we solve for the acceleration first before going to try and find something, before going to try and find the final velocity? It turns out we can. We know the final position, the initial position, and the initial velocity, and the time. If we look at this second equation here, there's the final position, initial velocity, which we know. The time, the only thing we don't know is a. So we're going to try this. We're going to write down the full equation first. X equals x naught plus v naught t plus 1/2 a t squared. We're going to cross off the things that we know are 0. Initial velocity is 0. Initial position is 0. That leaves me with this. The final position is 72 meters. The acceleration is unknown. And the time that it takes to go from 0 to 72 meters is 6 seconds. And I have to remember to square that. Now I just do order of operations and solve for a. 72 equals, let's see, 6 squared is 36 times 1/2. Half of 36 is 18. So that's 18a. I divide both sides by 18. I get the acceleration is 4 meters per second squared. That's not what I'm looking for, though. I'm looking for final velocity. Now that I have the acceleration, I look back up here. I could do a number of things. I could use either this equation or this equation. I'm going to use this one. Initial velocity is 0. Acceleration is 4. Time is 6. That's a really easy solve. Initial velocity is 0. The acceleration is 4 meters per second squared. Time is 6. The velocity, the final velocity I should say, is 24 meters per second. Now again, there are other ways to solve that. I encourage you to try and find them. Finally, last one, a train screeches to a halt in 20 seconds, over which time it travels 500 meters. If a is assumed to have been constant, what is the train's initial velocity? This one is really tricky because there's only one way to solve this, okay? Now, we know the time and we know the final position. Again, we can assume the initial position is 0 meters. We're looking for the initial velocity. We don't know what that is. We do know, however, what the final velocity is. The final velocity, since the train came to a halt, must be 0. Now, here's how we're going to solve this one. It is based on the fact that there are two different ways to solve for average velocity. I'm going to use the one we have on the front first. Average velocity equals change in position or displacement over time. X minus x naught over t. This is one way to find the average velocity. The final position is 500 meters. That's how far the train traveled as it was trying to stop. We're assuming the acceleration was constant as it tried to stop. 500 meters. We're assuming that it started at 0 meters. Okay? The displacement while it was trying to stop was 500. Okay? The time it took was 20 seconds. Doing a little bit of math, 500 minus 0 is 500 divided by 20. This tells me that the average speed as the train slowed down was 25 meters per second. Now, I can use my new equation from up here. The average speed is equal to the sum of the final and initial speed, or the average velocity is equal to the sum of the final and initial velocities divided by 2. To figure out what the final velocity, or what the initial velocity was. We actually know the final velocity is 0 because the train came to a halt. So that's 0. And all I do is I plug in 25 meters per second for the average velocity. Initial velocity is v naught over 2. If 25 is half of the initial velocity, then the initial velocity must have been 50 meters per second. And again, the reason I'm having you memorize this equation is because there are times, and like in this example, where it is actually impossible to get this answer if you try and use these. The last thing I want to talk about very briefly are proportionalities. These are little shortcuts that you can use in order to make problem solving a little bit easier once you get used to all these different terms and numbers and equations. Okay? These are shortcuts. But they only work if the acceleration is constant. I'm going to list each one for you. Let's say the initial velocity of something is 0 meters per second, and you think you have to use this equation. Well, if v naught is 0, then that just cancels out, and look what you have. You have v equals a times t. The acceleration is constant. What that means is that t must be proportional to v, or probably a better way to say it, v is proportional to t. Proportional just means if something goes up by a certain amount, by a certain factor, the other thing goes up by a certain factor. So let me write that out. If t changes by a factor of, I'll just call it b, so does v. In other words, look at this equation. A could be anything you want. If t doubles, you multiply it by a, which can be anything you want, that's going to make v double. If t quadruples, that's going to make v quadruple. That's the definition of proportional. V is proportional to t. There's proportionalities for each of those main three equations we talked about. Here's another. If v naught equals 0 meters per second, and x naught equals 0 meters, then you take this equation, x naught and v naught are both 0, it simplifies to this. Now, there's a reason we're not writing these equations like this all the time, because a lot of times you will have an initial position and an initial velocity. But in the case that you don't, these shortcuts are really useful. Again, let's look and see what is constant here. 1/2 is just a number, that's constant, and we're assuming a is constant. This means that x is proportional to t squared. Now this one's a little trickier. Listen to what this one means. If t changes by a factor of b, then x changes by a factor of b squared. Now that one's a little tricky. All it's saying is that, let's say over here, if the time doubles, like the time gets 2 times as big, Think about what has to happen to the time. It has to get squared. So the time doubles, but then you have to square that. That part is going to end up being 4 times as big, which means the position is going to end up being 4 times as big. So if the time doubles, the position ends up being 4 times as big. If the time were to triple, let's see, then t is 3 times as big, but then you square it, it becomes 9 times as big. If the time triples, x becomes 9 times as big. Finally, for the last one, if v naught equals 0 meters per second and x naught is 0 meters, this equation reduces to this. V squared equals 2ax, and that leads to a proportion of x being proportional to v squared. With the same meaning, if v changes by a factor of b, then x changes by a factor of b squared. That's probably a little complex for you right now to understand. Oh, that's not really clear. It's probably a little complex for you to understand right now with all those proportionalities. We will work on that in class. I just want you to have a basic idea of what that means. We'll see exactly the effects of that when we do things in class. Okay? That's the basics on kinematics. The main things I want you to get from this is that we have these basic terms, we have them defined. We can use these terms to solve for different variables. And this is going to be important as we move on because physics is about making predictions and understanding how things are going to work. If you have any questions, let me know. Otherwise, next time we come back, we'll be talking about graphs. See you later.